Hello, friends, and welcome back to Moonlight Science, where we drift through big ideas in soft, sleepy circles. Tonight, we'll travel inward, past ocean and continent, past stone and shadow, toward a place no one has ever seen, Earth's blazing heart. Textbooks tell us the core is iron and nickel, molten and solid, roaring like a hidden sun. But there's a puzzle here. By several lines of logic, our core shouldn't exist the way it does. And yet it does, humming beneath our feet. So tuck in, breathe slow. Let curiosity glow as we slip, layer by layer, into the paradox at Earth's center. Deep beneath the crust we walk upon, far below the mantle that slowly churns heat through rocky currents, lies a secret that defies ordinary logic. Earth's core, our planet's inner engine, is a strange double world. Its outer layer is a raging ocean of molten metal, swirling and heaving like a silent metallic storm. But buried at its heart is something even more baffling. A solid sphere of iron and nickel. A crystal that should not be solid by any ordinary rule of physics. Down there, temperatures soar higher than the surface of the sun. Hot enough to melt any metal we know. Hot enough that iron should be liquid, everywhere, without exception. And yet, in this impossible furnace, the very center has frozen into an iron heart. How does something freeze in a fire? Scientists have spent decades trying to answer that question. And the deeper they dig, the stranger the story becomes. Yes, immense pressure plays a part. The weight of an entire planet squeezes the inner core so tightly that atoms are forced into solid order even under unimaginable heat. But pressure alone doesn't solve the puzzle. The boundary between liquid and solid within the core is far too crisp, too clean, almost like someone drew a perfect line between chaos and structure. That delicate balance suggests other forces at work. The chemistry of the core, the way elements mix or separate, and the flow of heat outward through the planet. Then there's the matter of timing. Evidence hidden in ancient magnetic rocks hints that the solid inner core may be surprisingly young, possibly less than 1 billion years old. If Earth is over 4.5 billion years old, that means for most of its life, the entire core was molten. Why did the inner core freeze so late? And if the inner core only recently began to crystallize, how did our planet maintain a magnetic field long before that? Because yes, there is the magnetic field, a shield that curls around our world like a protective cloak, deflecting solar radiation and allowing life to thrive. That shield is powered by motion in the liquid outer core. Convection currents created as heat tries to escape into space. But heat flow alone might not have been enough. Something had to keep the core restless, swirling. Something had to fuel billions of years of invisible protection. How did our engine keep running before its heart began to freeze? Each piece of this mystery, iron that separates itself perfectly, a solid center that freezes in fire, and a magnetic dynamo that never seems to rest, feels like a clue in a long and complicated detective story. The rocks beneath our feet carry whispers from the past. Earthquakes send signals that bounce and bend through the iron depths, offering hints in subtle tremors. Even the atoms themselves hold memories and isotopic signatures left behind from violent beginnings. And so our journey begins here, suspended in a puzzle, a core that by many predictions should have failed long ago, cooled too quickly, frozen too early, or collapsed into silence. Instead, it persists. It beats with a rhythm older than our continents. It makes compasses point north. It keeps auroras dancing on polar skies. It should not exist as it does. And yet it does, fiercely and beautifully, at the heart of the only home we've ever known. long before Earth had oceans or sky, long before mountains touched the clouds or forests breathed beneath the sun. There was only dust. A swirling haze of microscopic grains, silicates, metals, tiny flecks of carbon, drifted around a newborn star. Our entire world began as particles so small you could fit millions of them on a fingertip. And yet, within those grains lived the chemistry of everything to come. Inside this spinning protoplanetary disk, the earliest forces at work were simple ones. Static electricity made particles cling together, forming fluffy clumps that tumbled through the nebular haze. With each gentle collision, they grew heavier. Pebbles became boulders. Boulders became mountain-sized bodies called planetesimals, cosmic seeds of future worlds. But growth in space is rarely gentle for long. As these planetesimals gained mass, gravity joined the dance, and collisions turned violent. They smashed together at incredible speeds, releasing energy as heat. With every impact, the young planet grew hotter, and with every addition of mass, its gravity deepened, drawing more material inward. The solar system's nursery became a chaotic arena of destruction and creation, where worlds were built out of shattered pieces. Within these growing bodies, something remarkable began to happen. Heat. Lots of it. Some of that heat came from impacts, but another source burned deeper. Locked inside the building blocks of planets were short-lived radioactive isotopes, like aluminum-26, whose rapid decay released intense internal heat. These atomic furnaces melted rock from the inside out. For the first time, solid stone became liquid, and the ingredients of planets began to separate. Iron, dense and metallic, felt the pull of gravity more strongly than the lighter elements around it. In molten environments, droplets of iron began to sink, like beads of mercury slipping downward through water. Scientists call this process planetary differentiation, and it is the reason Earth became layered, crust above mantle above core. But the efficiency of this sorting is still astonishing. Somehow, iron did not simply gather. It concentrated into a sphere, deep at the center, as though the heart of the planet had always been destined to be metal. Why did the iron migrate so completely? Some researchers believe that sulfur and carbon joined the metal, lowering its melting point and helping it flow more easily. Others argue that molten channels formed, like rivers of metal, draining downward through cracks and conduits in the partially molten rock. However it happened, the result was profound. A young Earth with a hot molten core, long before the first solid crust cooled above it. As the growing world continued to collide with others, sometimes swallowing smaller planetesimals whole, it refined its structure. Continual bombardment churned its surface, vaporizing oceans of rock and occasionally resetting the clock on its layered anatomy. It was an era without peace, a time when the building of a planet meant surviving firestorm after firestorm. Eventually, as dust cleared and collisions slowed, the solar system settled into a more stable rhythm. Earth, battered but resilient, emerged as a roughly spherical world with a metallic heart, a blazing engine sealed beneath thousands of kilometers of rock. The stage was set. The core was born. But this creation carried with it a contradiction, because such a molten heart should have cooled quickly, losing heat and energy within a relatively short span of cosmic time. And yet, Earth kept its core hot, liquid, and alive. Something in those early fires had established a balance that would continue to defy expectations. A balance that would one day give rise to the magnetic shield above us, the continents beneath us, and the story of life itself. Deep inside the young Earth, where rock had grown hot enough to soften but not entirely melt, a strange storm began to fall. It wasn't rain made of water or clouds or anything the surface world would ever know. It was rain made of metal, liquid iron forming droplets that slid and streamed downward through a churning mantle. Imagine molten beads glistening in the dim glow of a magma ocean, gathering into rivulets that sank like shimmering tears toward the planet's center. This iron rain was one of the most important downpours in Earth's history, though no eyes existed to witness it. As the proto-Earth heated from violent collisions and radioactive decay, its interior reached a critical tipping point. Rock began to melt just enough for iron to break free from silicates, those lighter minerals that would one day build continents and ocean floors. Tiny metallic droplets separated out, buoyed not upward but downward, pulled relentlessly toward the deepest gravitational well. At first, they trickled like dew along grained boundaries of partially molten rock, slipping through microscopic seams in a colossal stone sponge. But as temperatures climbed and regions of molten rock pooled, the droplets joined forces, merging into streams, then rivers, then great underground waterfalls of glowing metal. Here, a puzzle emerges, one that geophysicists still wrestle with today. For iron to gather so efficiently into the core, much of the mantle would have needed to be molten, at least for a time. But some evidence suggests that the entire Earth was never uniformly liquid all at once. So how did iron separate so completely if the planet wasn't a perfect ocean of magma? How did metal find pathways downward through rock that still held its shape? Experiments in labs, tiny worlds built in diamond anvils and lasers, give us hints. They show that iron mixed with sulfur or carbon melts earlier, flowing more freely and slipping faster toward the center. Simulations reveal how metal droplets can collect in dikes and veins, forming networks that funnel iron downward like underground plumbing. Each microscopic droplet was a traveler determined to reach the heart, and gravity was its guide. Still, this journey was far from smooth. Sinking iron heated the rock around it, carving hot channels that sometimes collapsed, redirecting the flow. Some droplets stalled, trapped in pockets of crystal-rich mantle, until a jolt of seismic energy or a shift in density freed them again. Chaos ruled the young Earth's interior. Yet out of that chaos emerged structure, a world finding its layers. With every droplet that reached the center, the metallic core grew. Each addition increased the gravitational pull, drawing even more iron downward. It became a feedback loop. The more metal gathered, the harder it became for any to stay behind. Slowly, a sphere of glowing alloy assembled, spinning beneath a world still being written. And in that growing heart lay the seeds of a future magnetic shield, one that would someday guard oceans, guide migrations, and paint auroras across polar skies. Iron rain might sound like poetry, but it was a force of nature with a purpose. It took a swirling cloud of stardust and helped shape it into a world capable of life. Elegant and improbable, that rain never truly stopped falling. Even now, deep beneath our continents, tiny droplets continue to migrate downward, joining the core's restless sea. Each one a reminder of a storm that forged the beating heart of Earth. Just as Earth was settling into its layered identity, chaos returned from the dark. A wandering world, about the size of Mars, crossed paths with our planet. We call this intruder Theia. It did not graze Earth politely. It struck with such force that the entire crust and upper mantle ripped apart in a flash of cosmic violence. For a moment, Earth was less a planet and more a swirling fireball of vaporized rock. Molten fragments were thrown into orbit, circling like glowing embers. From this chaos, gravity sculpted a companion, the moon, forever locked in Earth's sky as a reminder of the day our world was shattered and reborn. That colossal collision didn't simply reshape Earth's exterior. It rewrote the story of its interior, too. Temperatures spiked so high that huge portions of the mantle melted entirely if they weren't already molten. Metals and silicates mixed violently, then rapidly separated once more as the planet began to cool. This may have been the final push that drove nearly every last droplet of iron into the core, finishing the job that Iron Rain had begun. Some scientists argue that without Theia, Earth's core may have remained patchy or incomplete. A less efficient engine may be too weak to power a magnetic field billions of years into the future. Others propose a more complicated picture. Perhaps not everything melted at once. Maybe parts of the mantle remained solid, resisting mixing, leaving pockets of ancient chemistry still detectable deep within the Earth today. The core, too, may have swallowed different ingredients during this violent remix. More silicon, maybe more oxygen, changing its density and behavior. These lingering uncertainties are why the Moon holds such fascination for geochemists. Its rocks bear fingerprints nearly identical to Earth's mantle, suggesting that the collision mixed both worlds thoroughly. And yet, tiny isotopic differences whisper that Theia still left its mark. Whatever the exact recipe, one truth stands firm. Earth emerged from this catastrophe hotter than ever before. Its surface was a molten ocean of lava stretching horizon to horizon, glowing beneath a sky filled with vaporized stone. The atmosphere was thick with steam and metal-rich gas. The planet spun faster, days shortened to mere hours, and the core churned fiercely under the accelerated rotation. In this furnace-like newborn world, the seeds of future stability were paradoxically planted. Because a hotter, faster spinning Earth primes the core for long-term motion. The energy from that impact created a vast reservoir of heat that would take billions of years to escape. As the core gradually cooled, iron continued to sink and crystallize, driving currents in the liquid metal. Those currents twisted into spirals under the planet's rotation, giving rise to a magnetic shield that has lasted most of Earth's history. So from a strike that could have destroyed everything, came the conditions that preserved everything. Our moon, so calm and pale in the night, was forged from a moment of unimaginable chaos. And deep below us, the core it helped perfect still spins and roars, a molten testament to the ancient violence that built the only home we've ever known. The aftermath of Theia's collision left Earth wrapped in an ocean of fire. The surface was not land or sea, but molten rock, glowing and churning deeper than any ocean we know. From above, the young planet would have looked like a star more than a world, shining with heat that sought desperately to escape into space. At first, cooling was rapid. Radiation poured out from the exposed magma, and the planet's molten skin began to darken, forming a thin crust that cracked and sank as quickly as it appeared. But the pace of cooling soon slowed, caught in a delicate tug-of-war that almost defies belief. Above that fiery ocean, a thick blanket formed. Water vapor and carbon dioxide, released from melting rocks and degassing minerals, created a dense atmosphere that trapped heat like a colossal greenhouse. Volcanic eruptions continually refreshed this atmospheric shield, making it harder for radiation to escape. Earth had accidentally wrapped itself in insulation, and cooling became a careful negotiation rather than a simple slide into solid ground. The planet could not afford to cool too quickly. If heat drained from the core too fast, the inner core would freeze early, shutting down the dynamo that would one day protect life. Yet cooling too slowly carried an equal threat. Without a strong temperature difference between the molten core and the mantle above it, the churning currents needed for a magnetic field would weaken, and Earth's protective shield might have never sparked into existence at all. Somewhere in the balance of these contradictions, a planetary thermostat emerged. The surface began to fracture into plates of early crust, allowing pockets of heat to vent through volcanoes and fissures. The atmosphere swirled with storms that formed the first raindrops once temperatures dipped low enough for water to condense. Those rains fell into molten expanses, exploding into steam and thickening the atmosphere even more. But over time, as the sky cooled further, water remained liquid. Oceans gathered in the planet's hollows, spreading like blue skin over hardening rock. Water, too, became part of the thermostat. Liquid oceans absorbed enormous amounts of heat, then radiated it to space in long, slow breaths. Clouds formed and reflected sunlight. The first crust thickened into continents' ancestry. Each new layer of stability allowed the mantle to cool at just the right rate. Never too fast, never too slow. Inside the planet, radioactive elements continued to release heat, keeping the mantle warm and sluggish. Iron at the core remained molten, spinning beneath the cooling crust, yet not cooling so rapidly that the solid seed formed too soon. Cooling released energy. Not cooling enough preserved the engine's motion. It was a paradox that Earth somehow solved without consciousness, a balancing act beyond engineering, tuned by chance and nature. Eventually, the magma ocean hardened into the mantle we know today, though pockets of molten rock still linger deep within. Above it, the crust solidified into platforms that would one day drift as continents. Beneath it, the core remained a restless sea of metal. The planet had threaded the needle. It had cooled just enough to shape a solid world, yet remained molten at its heart. From the chaos of a world on fire emerged a planet suitable for oceans, for continents, for life, and for a hidden engine that still burns, impossibly and triumphantly, beneath every step we take. Deep below the cooling mantle and crust, the core remained a furnace, hotter than the surface of the sun. Yet somehow part of it was solid. Iron, the very metal that melts easily in a foundry, had crystallized into a rigid heart under conditions no human could survive. The secret lay in pressure. Down where the weight of the entire planet presses inward, iron atoms are squeezed so tightly that they can no longer move freely, forced into tidy formation even while heat screams for them to melt. But understanding how this solid inner core forms and what shape that iron takes is a puzzle that continues to challenge the world's brightest scientific minds. On Earth's surface, iron prefers familiar structures, arrangements of atoms we can map and predict. But when you compress iron under millions of atmospheres, the rules start to bend. In high-pressure laboratories, scientists trap tiny iron samples between diamond anvils, the hardest material on Earth meeting the strongest forces found within it. Lasers heat the samples to core-like temperatures, and detectors peer through the diamonds to watch atoms shuffle into strange forms. Shockwave experiments go further, blasting iron with impacts that mimic the violent pressures of Earth's interior in split-second flashes. These experiments are glimpses into a world we cannot reach. But every result shifts the boundaries of what iron can be. For a long time, we believed that the inner core was made of hexagonal, close-packed iron, a crystal lattice with atoms stacked like oranges in a grocery pyramid. But recent discoveries suggest another structure may emerge under certain conditions: body-centered cubic iron, a framework that reshuffles atoms into a more open arrangement. Surprisingly stable when mixed with small amounts of lighter elements. The core may not be one uniform crystal at all. It might shift its structure over time, growing in different phases that mingle, compete, or align in mysterious ways. Seismology, Earth's deep X-ray machine, adds another twist to the mystery. Seismic waves travel faster through the core from pole to pole than they do sideways across the equator. This directional speed-up suggests the inner core's iron crystals are aligned vertically, as though stretched by the flow of time and pressure. But how did they align? And do they match the forms produced in our tiny diamond experiments? There is tension between what we observe from above and what we produce in controlled labs. The key may lie in impurities, light elements dissolved into the iron like seasoning in a cosmic cauldron. Silicon or sulfur could shift the crystal structure. Oxygen, carbon, or even hydrogen could sneak into spaces between iron atoms, changing density and how vibrations pass through the metal. These tiny adulterants could be the very reason our inner core is solid, where theory says it should melt, or why it grows faster in one hemisphere than the other. Inside this impossible pressure cooker, matter writes poetry. Atoms arranged in patterns sculpted by gravity's unyielding fist. We cannot touch the core. We cannot see it. Yet every earthquake, every experiment, every simulation draws its portrait with a little more clarity. The inner core stands as a contradiction made real. Metal that shouldn't be solid, shaped into forms that shouldn't exist, beating like a hidden heart that keeps the world alive. The deeper scientists study Earth's core, the more it refuses to behave like a simple ball of iron. Seismic waves move through it too slowly. The density is too low. Something lighter stirs within that metallic ocean, an unseen ingredient that softens the core's weight and changes its personality. Pure iron alone cannot account for what our instruments measure. So the question becomes a mystery of chemistry. What else is down there, mixed into the fire? The suspects are subtle. Silicon, oxygen, sulfur, carbon, and hydrogen. 5 light elements with 5 very different stories to tell about Earth's birth. Each one carries a signature. Clues about the kind of materials that built our planet, the temperature of ancient magma seas, and the violence of the collisions that forged Earth's interior. And each one, if present, would shift the core's density in just the right direction. But none can be added freely. Too much sulfur and the core becomes too soft. Too much silicon and its seismic fingerprint no longer matches reality. We are trying to recreate a recipe without ever tasting the dish. To trace these ghostly elements, scientists don't look downward, they look outward and backward. Meteorites, fragments of dead planets, preserve the chemistry of the early solar system. By comparing them to Earth's rocks and metals, researchers try to piece together which ingredients went where during formation. Some meteorites, rich in sulfur, hint that early Earth may have swallowed metal laced with that element, driving iron to separate more easily and melt sooner. But sulfur alone can't explain everything we see. Oxygen presents a different problem. It strongly prefers to bond with silicon in rocky minerals, not with metal. For oxygen to dissolve into the core, iron and rock must have mixed intimately under crushing pressures during differentiation. If oxygen is in the core, it suggests a world melted so deeply that metal and rock exchanged atoms freely before parting ways again. But too much oxygen would make the core far too light, and seismic waves would travel even slower than they do now. Carbon, the element of life, may also play a part. Under intense pressure, it dissolves into liquid iron and forms iron carbides, materials that could exist in the core today. Some scientists even dream of diamond rain forming at the boundary between core and mantle, as carbon-rich material floats upward and crystallizes into shimmering solid drops. Yet carbon's life cycle is written in volcanic outgassing and deep mantle minerals, and its budget must match the reality we observe at the surface. Then there is hydrogen, the smallest atom, able to slip into spaces between iron atoms like a quiet stowaway. If early Earth swallowed enough water, hydrogen could have hitched a ride into the core as iron descended. Even a little hydrogen can change density dramatically. But hydrogen would also tweak conductivity and melting temperatures in ways the geodynamo might not tolerate. The challenge is this: all these elements can influence the core's density, sound speed, and heat flow. But the blend must satisfy every clue at once. Too much of anyone breaks the model. Too little, and the mystery remains unsolved. Somewhere, deep underfoot, lies the perfect mixture. Delicate, balanced, improbable. In that mixture is hidden the truth of how Earth became a world with a molten heart. A heart that shouldn't be liquid, shouldn't be solid, shouldn't be magnetic. And yet is all three at once, because of a secret recipe forged in the planet's fiery youth. The light elements we cannot see keep the core alive, stirring iron into motion and powering the shield that protects every living thing on Earth today. Deep beneath the crust and mantle, in a realm where rock gives way to metal and pressure squeezes atoms into strange alliances, something extraordinary happened. The molten outer core, rich with iron and sprinkled with those mysterious light elements, began to move. Heat leaked outward into the planet above, and as metal cooled, it sank. Hotter metal rushed upward to take its place. This constant overturning created vast, swirling currents. And in a conductive liquid like iron, motion and electricity intertwine. Flowing metal sheared and twisted into spirals, generating not just heat, but something far more powerful: a magnetic field. This was the birth cry of Earth's invisible shield. A magnetic field might seem like a simple byproduct of moving metal. But dynamos, the engines that generate these fields, are delicate. They demand just the right conditions. The core must lose enough heat to keep convection vigorous, but not so much that it freezes solid too quickly. It needs composition gradients, light elements rising, heavy ones sinking, to help drive motion even when heat flow threatens to slow. These requirements form a narrow corridor, a fine-tuned balance the Earth has somehow maintained for billions of years. The inner core plays a starring role in this dance of survival. As it slowly freezes from the inside out, it releases two powerful forms of energy: latent heat and buoyancy. Just as ice forming on a lake releases heat into the surrounding water, crystallizing iron releases energy that fuels convection in the liquid metal around it. And as that solid iron grows, it pushes lighter elements, like silicon and oxygen, out into the outer core, making them float upward like tiny balloons. These upward flows churn the metallic ocean, keeping the dynamo spinning. Above the core, the mantle acts as a gatekeeper of heat. It cools through plate tectonics, continents shifting, seafloor spreading, volcanoes venting heat from below. Every time a tectonic plate dives into the mantle, it carries cold rock downward, drawing heat from the core. Without this planetary recycling system, the mantle might act like a thermal blanket, slowing the core's cooling too much. Plate tectonics, storms of rock that move no faster than fingernails grow, has been one of the greatest protectors of Earth's magnetic heartbeat. The magnetic field created by this restless core is a wonder all its own. It reaches far beyond the atmosphere, carving out a protective bubble in the solar wind. Charged particles from the sun, capable of stripping atmospheres and sterilizing surfaces, are deflected away, curling along invisible field lines. Without this shield, Earth's oceans might have boiled away like those on Mars. Without this shield, life may never have found safe ground to flourish. Yet the magnetic field is not fixed. It pulses, it wobbles, it reverses direction from time to time, flipping north and south like a cosmic coin toss. These reversals are evidence of the dynamo's chaotic beauty, restless currents that never exactly repeat themselves. And still, the field persists, never quiet for long. What stuns scientists most is its endurance. For nearly Earth's entire history, over 3 billion years, the magnetic field has refused to die. The core continues to churn. The inner core continues to grow. The mantle continues to cool at just the right rate. And high above, the auroras dance in shimmering curtains, revealing where invisible forces meet the sky. Beneath our feet, the impossible engine spins on, unseen but essential. It may be the most important part of our world that we will never touch. A hidden guardian, forged in fire, shaped by pressure, and kept alive by the careful balance of a planet learning how to protect itself. Earth keeps its deepest secrets well hidden, sealed beneath thousands of kilometers of solid rock and molten metal. No human instrument or machine will ever bore a path directly into the core. The pressure alone would crush a steel like clay. But the planet has its own messengers, vibrations that race through its body every time it trembles. Earthquakes, though they may frighten us on the surface, are gifts to science. Each one sends ripples of information echoing through the planet's interior, writing invisible sketches we've learned to read. When a major quake strikes, it releases two primary types of seismic waves: P waves and S waves. P waves are compressional. They push and pull like the beat of a drum. They can pass through solids, liquids, and even gases. S waves are shearing, moving side to side like shaking a rope. They travel only through solids. As these waves travel outward from the source of a quake, they bend and bounce, speeding up through some layers and slowing through others. Sensitive instruments around the world pick up their arrival, recording precise timings on seismograms. By comparing when these waves arrive at different locations on Earth, scientists began to decode an astonishing truth. S waves never appear on the far side of the planet after passing through the deep interior. They vanish into a forbidden zone. The reason was startling. They cannot travel through the core's outer layer. That region, they realized, must be liquid. Meanwhile, P waves took curved paths, bending more than expected as they plunged deep inside the planet. This bending revealed changes in density, marking boundaries between mantle and core. And eventually, the moment when P waves passed from liquid metal into something solid again. Hidden at the center was a solid inner core. It was like discovering that Earth had a second world tucked inside, one we had never felt beneath our feet. But the story becomes stranger. Not all seismic waves move evenly through the inner core. Waves that travel north to south do so faster than those moving east to west. This anisotropy hints that the iron crystals in the inner core are aligned, perhaps stretched by the same forces that drive Earth's deep rotation. Even more curious are hints that the inner core might have distinct hemispheres, one softer or slightly younger than the other, as though crystallization began unevenly or changed course midway through the planet's history. Some seismic signals even whisper of a blurry zone, where the solid inner core meets the liquid outer core, a mushy transitional layer, neither fully frozen nor fully molten. If true, this layer could reshape our understanding of how the core cools, grows, and powers the magnetic field above. Each discovery from seismic data adds complexity to a picture we cannot see, only hear. Earthquakes speak in inaudible tones, and we have learned to translate those vibrations into architecture. The planet's interior becomes a symphony of echoes. upward reflections from secret boundaries, subtle tremors revealing crystalline textures, and shadow zones marking liquid realms below. Our world is not silent. Every quake is a conversation from the depths, a coded message carried to the surface at thousands of meters per second. By listening, patiently, carefully, we have mapped the unreachable. The core remains untouchable by drill or camera, yet through tremors alone, we've uncovered its molten seas, its solid heart, and the peculiar behaviors of iron under impossible pressure. In every rumble beneath our feet, the Earth continues to tell us its story, one vibration at a time. Beneath the swirling molten ocean of the outer core lies a hidden world of iron crystal, Earth's inner core. For decades, we pictured it as a simple, solid sphere, smooth and uniform, like a metal ball bearing at the center of our planet. But the more we listen to the language of seismic waves, the more that picture fractures into complexity. The inner core, it turns out, has texture, personality, and perhaps even motion of its own. Seismic waves traveling through the inner core behave differently depending on their direction. Waves moving from pole to pole travel faster than those moving across the equator, hinting that iron crystals deep inside may align like fibers in wood, an entire crystalline structure stretched along Earth's rotational axis. This alignment likely emerged over millions of years, shaped by the stresses of growth and the flow of liquid iron around it. Imagine a buried crystal being forever pressed and twisted by convection currents, slowly developing a preferred orientation. But the mysteries go deeper. Data suggests that one side of the inner core, the hemisphere beneath the Pacific, looks different from the hemisphere beneath Africa and the Atlantic. One seems softer, or perhaps younger. It's as if the inner core has an Eastern and Western identity, two halves growing at slightly different rates or under different chemical conditions. The boundary between these personalities is not sharp, but its influence echoes through seismic readings like a hidden scar. How could such asymmetry form at the center of a world striving for balance? One possibility is uneven heat loss. Where the mantle above draws heat more vigorously, the core below may freeze more quickly, adding fresh iron crystals that push outward unevenly. Over geological time, this could tilt the crystal structure, layering the inner core like growth rings in a tree, rings that record shifts in Earth's deep climate. Even more astonishing is the possibility that the inner core rotates at a different speed from the rest of Earth. Some studies suggest it turns slightly faster, completing one extra rotation every few decades. Others hint that it may lag behind or oscillate like a pendulum. How can a solid heart spin within a liquid sea? Electromagnetic forces may gently tug at it, while the flowing outer core drags or nudges it along. The iron is solid, yes, but not rigid. Under unimaginable pressure and heat, it creeps slowly, reshaping itself like a glacier made of metal. This textured, layered, rotating heart raises another question. When did the inner core begin to form? The best clues suggest it may be less than 1 billion years old, a relatively recent addition in Earth's 4.5 billion year story. But if the magnetic field depends on energy from inner core growth, how did the dynamo survive for billions of years before that? The answer lies in chemistry. When Earth first differentiated, light elements were forced out of the metal as it segregated from rock. Those buoyant elements rose through the outer core, stirring currents like invisible paddles. For billions of years, chemical convection powered the magnetic field, long before solid crystals began to grow at the center. And so, the inner core is not merely the planet's heart. It is a diary written in iron, recording pressure, chemistry, and the restless flow of time. It grows unevenly, spins subtly, aligns its crystals like iron forests, pointing toward the poles. It remembers when Earth was hotter, when the magnetic shield flickered toward life's dawn, and when the balance of heat and chemistry chose to freeze fire into structure. It is a solid miracle surrounded by molten power, still evolving in darkness, an iron seed whose secrets continue to pulse outward in every tremor beneath our feet. Far below Earth's surface, where the rocky mantle plunges into heat so intense that minerals begin to shimmer and distort, there lies a boundary unlike any other. It is not a sharp dividing wall, but a turbulent coastline, a place where rock meets metal, where solidity meets liquid fire. Scientists call it the core mantle boundary, or simply the CMB, but that name barely hints at its drama. This is Earth's most chaotic frontier, a hidden border that plays referee between the furnace below and the cooling world above. Imagine standing on a cliffside that overlooks an endless metallic ocean. Beneath you, liquid iron churns in dark, swirling currents. Above you, the mantle looms as a world of slow-moving stone. Pressures here crush atoms into strange alliances, and temperatures could vaporize anything familiar. It's a boundary defined by contrast. Rock sitting atop a sea of molten metal. Yet the two interact constantly, exchanging heat and chemical whispers that shape the planet as a whole. Seismic waves reveal that the CMB is far from smooth. Pockets of rock their slow seismic vibrations to a crawl, regions known as ultra-low velocity zones. Scientists believe these patches may contain partially molten rock, melted by the scorching heat of the core. Elsewhere, two enormous continent-sized structures rise off the core like submerged plateaus. These LLSVPs, large, low shear velocity provinces, are denser and chemically different than their surroundings. They might be ancient mantle leftovers or accumulations of ocean crust dragged downward by subduction. Whatever their origin, they act like thick blankets, insulating the core below and altering how heat escapes into the mantle. This uneven heat flow is far more than a temperature concern. It governs the strength and style of the magnetic field. Where the mantle draws heat efficiently, the liquid core below becomes restless. Convection intensifies, and magnetic field lines strengthen, twist, and reorganize. Where mantle structures trap heat beneath them, the convection weakens and the dynamo slows. The geodynamo, that delicate and powerful engine, depends on this heat exchange like breath. Above these hidden features, on the planet's surface, continents drift across millions of years. Yet their wandering footprints seem to align with magnetic field anomalies recorded in rocks. It's as though the deep Earth weather at the CMB, its hot spots and cold trenches, imprints patterns that stretch all the way to the crust. When a supercontinent parks above a sluggish region of the mantle, heat backs up at the boundary below, shifting flow patterns in the core. Compass needles eventually feel the consequences. Even magnetic reversals, those times when north becomes south, may be nudged into motion by what transpires at this buried shoreline. Meanwhile, the cycle of plate tectonics works both ways. Subducted slabs plunge into the mantle and may sink all the way to the CMB, where they deliver a cold shock that ramps up heat loss from the core. Columns of buoyant rock, mantle plumes, may rise from boundary hotspots, feeding volcanoes at the surface. Hawaii, Iceland, and other volcanic islands could be the distant, fiery punctuation marks of events happening just above the metal sea at Earth's center. The CMB is a throttle and a brake. If heat escapes too quickly, the core might freeze young and silent. If heat is trapped too tightly, the dynamo could starve and falter. Somewhere between chaos and equilibrium, the boundary regulates the heartbeat of the magnetic field. We rarely think of compass needles as delicate. We forget that aurora borealis depends on physics unfolding thousands of kilometers below our feet. But every shift in Earth's magnetic moods, every flicker in its shield, can be traced back to that stormy border where rock and metal negotiate the fate of the planet. In that hidden turbulence, the future of Earth's heart is always being decided. Beneath the surface calm of continents and oceans, Earth's magnetic field pulses like a living thing. It is not constant. It wavers, weakens, rebuilds, and every so often, it flips. North becomes south, south becomes north. These magnetic reversals, scattered throughout the rock record like breadcrumbs, are reminders that the invisible shield wrapped around our planet is no steady guardian, but a restless one. On average, such flips occur every few 100,000 years, though the timing is irregular. Sometimes the poles switch rapidly. Sometimes they linger in a transitional haze. And yet, one truth remains astonishing. Even during its most chaotic episodes, the magnetic field refuses to die. When a reversal begins, the field weakens dramatically. If we were alive to witness the start of one, we might see auroras wander toward the equator and satellites struggle without their usual protection. Migratory animals, guided by magnetic cues, would find the world strangely confusing. But despite this fragility, the field does not vanish into silence. It becomes tangled and multipolar, no longer a clean dipole with one north and one south, but a swirling ballet of temporary poles scattered across the planet. Like a beating heart caught in an arrhythmic episode, the dynamo keeps functioning even while reorganizing itself. We know this from the rocks. When lava cools, minerals within align with the direction and strength of Earth's magnetic field at that moment. These frozen compasses record magnetic history with remarkable fidelity. In places like Hawaii and Iceland, long stacks of ancient lava flows reveal fields pointing in every direction imaginable, evidence of reversals caught mid-spin. Some flows show weak, chaotic signals. Others show new poles forming far from their usual positions. The field was confused, but not extinguished. How can something so chaotic remain so resilient? The answer lies deep within the molten outer core. Even when the large planet-spanning convection patterns shift and collapse during a reversal, smaller circulations survive. The dynamo doesn't depend on a single organized flow, but on countless swirling eddies, big and small, each contributing to the magnetic orchestra. When the global conductor falters, the ensemble continues. Tiny patches of magnetic order persist until the system reassembles itself into a new pattern. In other words, the field can fall apart and recover at the same time. This resilience speaks volumes about the vigor of the core. It must be churning with enough chaotic energy to ensure a near-constant supply of magnetic seed fields. Small sparks ready to be amplified once the main structure chooses a new orientation. Reversals may feel dramatic from a geological perspective, but to the core, they are simply moments of reorganization, opportunities to refresh the field's geometry. There is a paradox in this behavior. A system that looks precarious is, in fact, incredibly hard to shut down. The magnetic field may flicker, fade, or go wild, but it keeps returning again and again, as though the planet refuses to let go of its shield. Even when the compass loses its mind, the core does not. It keeps humming in the dark, beating out a rhythm that has lasted billions of years. A reminder that deep inside Earth, persistence lives in molten metal, not in silence. Sulfur is one of the most elusive characters in Earth's interior drama. It's not heroic like iron, not flashy like carbon, not structurally commanding like silicon. Instead, sulfur plays its role in shadows, subtle, transformative, and sometimes disruptive. If iron is the core's foundation, sulfur is the quiet architect reshaping the rooms from within. By joining iron under intense pressure, sulfur lowers the metal's melting point, making the outer core easier to keep liquid. That sounds helpful for sustaining the geodynamo. But sulfur can also lighten the core's density and even separate into layers, changes that may complicate the flow of heat and metal currents. It is a double-edged ingredient, enabling motion on one hand and suppressing it on the other. Consider the early Earth after its fiery birth. The core was freshly formed, simmering with leftover heat from accretion and impact. As the planet cooled and the lighter elements began to drift upward, pockets of iron enriched with sulfur could have gathered near the top of the outer core. These lighter metallic mixtures might have refused to sink, forming a stable gravitational lid, a stratified zone where convection slowed or even paused. Such a lid would act like insulating ceiling tiles over a metal ocean, trapping heat below while muting the churn above. Convection beneath it would struggle to break free. The dynamo could falter, patterns in the magnetic field could warp, and heat might dam up in the liquid interior. If the inner core hadn't yet begun to grow, or hadn't started expelling buoyant light elements into circulation, the geodynamo's survival would hang on a knife edge. This hypothetical sulfur-rich layer could also have formed much later, as the inner core crystallized. When solid iron freezes, it rejects impurities, including sulfur. Those impurities would rise upward, pooling at the top of the outer core. With enough accumulation, the liquid there could become compositionally distinct, and layers might form once again. We imagine a world where the core is not one sea of molten metal, but multiple strata, each swirling to its own tempo, each changing the music of the magnetic field above. Evidence for these hidden compartments comes from seismic waves that hesitate strangely near the top of the outer core, from magnetic maps that show patches of persistent weakness or unpredictability, and from geochemical hints that Earth's earliest magnetic field may have flickered before the inner core took its current role as the dynamo's power source. But sulfur does not always win. Heat is a ruthless equalizer. If enough energy is driven upward, perhaps by sudden mantle changes or by changes in inner core crystallization, those layers can be peeled apart like old wallpaper. Instability returns. The orchestra rises together again, and the magnetic field strengthens. In the end, sulfur reminds us that Earth's core is not a simple sphere of metal. It is layered, dynamic, and alive with tension. Iron gives it strength. Heat gives it motion. But sulfur gives it doubt, an undercurrent of instability that makes the core feel astonishingly close to failure, even as it continues to triumph beneath our feet. Oxygen is the element we most associate with life. Breathing lungs, rusting iron, the invisible half of every drop of water. But deep below our feet, where life cannot go, oxygen may play a different role altogether. In the underworld of the core, it is not a giver of breath, but a shaper of metal, a mischievous ingredient hiding where it supposedly does not belong. Under ordinary conditions, oxygen has a strong preference. It clings to silicon in rocky minerals, building the silicate world of the mantle and crust. But when pressures climb to millions of atmospheres, when rock softens into magma and metal becomes liquid lightning, chemical loyalties shift. Oxygen may dissolve into iron after all, slipping between atoms like a whisper. If oxygen did join the core early in Earth's history, it would help answer several mysteries that have puzzled geophysicists for decades. It would lighten the outer core, which seismology tells us must be less dense than pure iron-nickel alloy. It would alter sound speeds in just the right direction, making seismic waves behave the way they do as they echo through the planet. And when the inner core later began to freeze, it would push oxygen outward, fueling a form of chemical convection that keeps the metallic currents alive and the magnetic field strong. Yet oxygen brings complications. Too much of it would make the inner core's density mismatch with observation. Too little, and it fails to provide the buoyancy needed to drive the dynamo over billions of years. Every proposed amount must walk a tightrope between benefit and contradiction. Like adding salt to a recipe where a single grain too many ruins the dish. Scientists test these possibilities using the most extreme laboratories on Earth. Inside diamond anvil cells, iron and oxygen are crushed to the pressures of the deep interior, while lasers blast them to sun-like heat. In these micro-worlds, droplets of metal and silicate try to separate. Sometimes, oxygen follows the silicate phase. Sometimes, surprisingly, it remains with the metal. Evidence that the core may carry more of this volatile ingredient than once believed. Other experiments rely on shock waves, tiny, controlled explosions that fling matter into momentary states found only thousands of kilometers down. Or they use microgravity aboard orbiting labs to watch molten iron drip through silicate without settling into predictable layers. Each new test shifts the boundaries of what seems chemically possible at Earth's center. But like sulfur and silicon, oxygen is likely only part of the answer. Too neat a solution rarely survives the scrutiny of seismic data, magnetic history, and planetary evolution. The emerging picture suggests a blend. Oxygen entwined with silicon, maybe a hint of hydrogen threading through the alloy. A cocktail of elements that together deliver just the right density, conductivity, and melting behavior to sustain a liquid core, far longer than simple iron could manage. Oxygen's role in this story is not dramatic or commanding. It is quiet, subtle, the shadow behind the light. Yet it may be one of the reasons our core has not frozen solid, why the magnetic field persists, why life can walk the surface without being stripped bare by solar wind. A planet's heartbeat depends, in part, on a breath it never takes. Silicon is everywhere on the surface of Earth. It builds sand and mountains, computer chips and gemstones. It is the backbone of the crust and mantle, an architect of everything solid beneath our feet. For a long time, we assumed its work ended there. But as we followed seismic clues into Earth's deeper layers, we began to suspect that silicon has been working behind the scenes much farther down, quietly shaping our planet's heart. Unlike oxygen, which clings to rock until extreme pressures pry it loose, silicon seems more willing to cross the boundary into metal when the environment becomes wild enough. During Earth's earliest, hottest chapters, the young planet was a roiling vat of partially molten rock and metallic droplets. Under those conditions, high temperatures could blur the chemical lines between metal and silicate. Silicon atoms, normally bound in rocky frameworks, may have dissolved into the metallic iron just as the core began to form. Meteorites, fragments of other ancient worlds that also differentiated, support this idea. Some metallic meteorites contain traces of silicon, a hint that core formation throughout the solar system often recruits this versatile element. Silicon would have changed the core's personality in important ways. It lowers density slightly, but not too much, keeping the core consistent with seismic measurements. It alters how sound waves travel through iron, helping to explain why seismic waves behave as they do as they cut through Earth's deepest regions. It transforms conductivity and melting behavior just enough to help maintain a liquid outer core that refuses to freeze prematurely. Too much silicon would break the physics we observe. Just a little, however, makes everything fit together more cleanly. But silicon's role must be balanced with the needs of the mantle above. The mantle is already swimming in silicon. If too much sank into the core, the mantle's chemistry would look stripped and distorted. Yet, ancient rocks show no sign of such a theft. That means silicon's entry into the core must have been modest, controlled, and maybe temporary. A likely story begins after the Theia impact, when Earth was wrapped in a global magma ocean. High temperatures allowed metal and silicate to mix intimately. Silicon found itself equally comfortable in both worlds. But as the mantle began to cool and crystallize, silicon was pushed out of the rockier regions and into the metallic depths, only later to be partially extracted again through the slow growth of the inner core. In this view, the core began life with more silicon than it has today. Over billions of years, the freezing iron heart has expelled some silicon back upward into the liquid outer core, like a gardener pruning a tree from within. Silicon's influence is never loud. It does not announce itself the way sulfur does with stratified layers or oxygen does with density riddles. Instead, it acts as a fine-tuning mechanism, adjusting the core's density gently, smoothing out mismatches, aligning calculations with reality. It is a quiet architect, making sure that heat flows, waves travel, and the metallic ocean remains mobile enough to sustain the dynamo's pulse. Our survival depends on a chain of improbable balances. Heat neither kept nor lost too quickly, iron neither wholly liquid nor fully solid, a magnetic field neither permanent nor fragile. Somewhere in that precarious dance, silicon plays its subtle part, blending into the heart of the world, ensuring that the core that shouldn't exist does. Because even deep beneath the mantle's crushing silence, the smallest decisions of atoms matter. Carbon is a storyteller element. At the surface, it shapes every living thing, bones, leaves, oceans of plankton, and rests in ancient archives like coal and limestone. But deep below the continents and seas, far removed from biology, carbon may have written an entirely different chapter in Earth's history. A chapter not of life, but of fire and metal. In the early molten stages of planet formation, carbon did not care about cells or ecosystems. It followed the pull of chemistry and pressure, dissolving into iron when permitted, staying with silicates when forced. Under intense heat, iron and carbon can bond into iron carbides, solid, dense compounds that behave unlike either of their parents. Some researchers believe that when Earth's core first formed, carbon slipped into the metal and altered its behavior in ways that helped shape the world we know. One possibility is that carbon lightened the core ever so slightly, contributing to the density deficit that seismic data demands. Another is that carbon shifted the melting temperature of iron alloys, making it easier for the outer core to remain liquid even as the planet cooled. Carbon is a subtle influence, never the main ingredient, but a quiet modifier helping ensure that the engine beneath us stayed fluid and alive long enough to power a magnetic shield. But carbon's journey didn't end in the core. As inner core crystals grew, they may have expelled carbon upward, where it would rise through the outer core and accumulate at the frontier between metal and rock. There, at the core mantle boundary, conditions become strange and exotic. Carbon-rich liquid, meeting cooler and chemically different silicate rock, might crystallize into one of nature's hardest and most dazzling minerals. Diamond. Imagine it. Billions of years of gentle chemical currents lifting carbon upward, where pressure and temperature conspire to transform it into glittering solid rain. tiny diamonds forming and sinking again, collecting into hidden reservoirs. Some of Earth's deepest mantle diamonds, formed under impossible conditions, may be evidence of this eternal cycle. Jewels born from the core's breath. Of course, Earth's carbon inventory must also satisfy what we see at the surface. Volcanic eruptions release CO2 that once was buried deep. Diamonds brought up by volcanic pipes glitter with stories of ancient chemistry. And mantle rocks reveal subtle fingerprints of carbon that has traveled through our planet's interior for eons. Each clue suggests carbon is not confined to the crust and biosphere. It moves through every layer, including the metallic heart. If carbon's presence in the core is real but modest, then its role becomes that of a balancing weight. Not enough to steal the spotlight, but enough to tip the scales toward a world where the outer core remains liquid longer, where the inner core's growth is gradual, and where the magnetic field can endure. Carbon is the ghost at Earth's center. Invisible, powerful, and eternal. It reminds us that the boundary between the chemistry of life and the chemistry of planets is thinner than we once imagined. The same element that builds bodies and forests may also help sustain the protective shield that makes life possible in the first place. In a world where fire freezes and pressure carves diamonds from darkness, carbon has never stopped shaping the fate of the Earth. Hydrogen is the quietest of elements. Light, elusive, almost impossible to pin down. At the surface, it dances in water molecules, drifts into the sky, fuels sunlight in the hearts of stars. But deep inside Earth, where temperatures scorch and pressures crush, hydrogen may be doing something far more surprising. It may have slipped into the metallic core, becoming part of the hidden engine that shapes our world. In the early solar system, water was plentiful in the form of icy grains, hydrated minerals, and wet planetesimals, the building blocks of planets. When Earth formed, it did not remain dry. Impacts delivered oceans' worth of water, and some of that water was dragged downward as metals separated from rock. Under sufficient heat, water breaks apart. Oxygen bonds to iron or silicate, while hydrogen, the tiniest atom, diffuses like vapor through the cracks of matter itself. Hydrogen can do what larger atoms cannot. It sneaks between iron atoms, occupying spaces too small for anything else to fit. Under extreme pressures, it forms iron hydrides, metallic alloys where hydrogen hides inside iron's crystalline cages. This changes everything. The mass of the core, the way seismic waves travel through it, how heat and electrons move. Hydrogen makes iron behave like a newly invented substance, one that is lighter and perhaps more fluid than iron alone. This could help explain why the core is not as dense as pure iron demands. Just a trace of hydrogen, parts per thousand or even parts per million, would be enough to provide the missing buoyancy that seismic models require. Hydrogen's feather-light touch could help keep the outer core molten, ensuring that convection continues and the magnetic field remains alive. But hydrogen is a tricky partner. Too much and the core becomes too light. Seismic waves would speed up or slow down in ways that do not match what earthquakes reveal. The magnetic field might behave differently, or cooling rates could shift, threatening the long-term survival of the dynamo. So if hydrogen is indeed part of the core's secret recipe, its portion must be precisely measured by the blind hands of nature. Scientists chase hydrogen's deep signature using laboratories that mimic the core's brutal conditions. Diamond anvil cells crush iron and hydrogen together, while lasers heat them to thousands of degrees. Shock compression experiments blast samples in microseconds, freezing behavior into data before the material vaporizes. Each result brings new insights, yet also new questions. How stable are these hydrides at the temperatures of the core? Do they cluster or disperse? Do they rise toward the outer boundary or sink toward the inner heart? Hydrogen's presence in the core would also link the fate of the deep Earth to the history of the oceans. Perhaps the first waters delivered to Earth did not stay at the surface, but plunged downward, seeding the core with the smallest atom in nature. Perhaps some of the hydrogen locked away in that metallic sea has been there since the world's earliest dawn. Even whispers of hydrogen can have a loud impact inside a planet. It shifts the balance of pressure and melt, density, and motion. It keeps iron lighter, convection stronger, and possibilities alive. If hydrogen truly dwells in Earth's core, then life's most essential element is also part of the great metallic heart that protects life itself. In the end, hydrogen reminds us that the core's persistence, the molten truth beneath us, is not a simple story. It is a symphony of elements, each playing just softly enough to keep the impossible alive. Deep beneath our feet, where atoms are squeezed so tightly they can barely vibrate, a strange miracle is unfolding. A star is freezing from the inside out. Earth's inner core, small, dense, brilliant with heat, was once entirely liquid. But as our planet slowly cools through the ages, iron begins to crystallize at the very center, forming a solid seed wrapped in a swirling metallic ocean. It is like watching a drop of frost form at the heart of a flame. This inner core is not merely a passive object. Its growth is power. When iron solidifies, it releases latent heat, the same warmth hidden inside steam when it condenses to water. At the same time, lighter elements are expelled into the outer core, creating buoyant chemical forces that stir the metallic fluid above. These two engines, thermal and compositional, drive the geodynamo, the process that sustains Earth's magnetic field. Without this ongoing crystallization, the dynamo would weaken, and the field that shields us from cosmic radiation might flicker and fade. Yet the inner core's birth is wrapped in mystery. Estimates of its age vary wildly. Some place its formation as early as 1 billion years ago. Others suggest it is barely a few 100 million years old. This uncertainty matters because the timing must match the story told by ancient rocks. Paleomagnetism, fossil magnetism trapped in solidifying lava, reveals that Earth has wielded a magnetic field for at least 3.5 billion years. So if the inner core is a youngster, then something else must have powered the field before it appeared. That something was likely a chemical storm. The expulsion of light elements during the core's initial formation created enough buoyancy to fuel convection for eons, until the planet cooled enough for solid iron to finally take hold. When that moment arrived, crystallization did not proceed gently. It likely began unevenly, crystals branching like metallic snowflakes, forming dendrites that interlock into a growing mass. The boundary between solid and liquid may not be sharp but smeared into a mushy transition zone, where iron grains jostle in slush. This texture is not merely academic. Seismic waves move faster through the inner core along the planet's spin axis than across it, anisotropy written into the metal. One explanation is that the iron crystals align as they form under convection and planetary rotation, pointing their strongest directions toward the poles. The inner core may be slowly spinning at a different rate than the mantle above, a separate world turning within our world, nudged by magnetic torques and slowed by friction. The hemispheres of the inner core also appear mismatched. The eastern side seems younger or softer, while the western side appears older or more rigid. Perhaps the inner core freezes unevenly, growing faster in one direction and then flowing or deforming to compensate. Even as it solidifies, the core remains restless, changing shape, rotating, renewing itself in silence. Freezing a sun is not simple. It demands just the right cooling rate. Too slow and the magnetic field would starve. Too fast and the inner core would rush ahead, disrupting the balance that sustains Earth's protective shield. Yet, against impossible odds, our planet has threaded that narrow path for billions of years. At the center of Earth, iron is turning from fire into crystal, and in that transformation lies the heartbeat of the world. The core is a furnace that never sleeps, but it cannot burn on its own. It must shed heat into the mantle above, losing energy so that liquid metal keeps moving, rising and sinking in endless turbulent loops. This motion, the churn of a planetary engine, creates electricity and, in turn, a magnetic shield. But a dynamo, like any machine, has a diet. It needs fuel, and every calorie counts. The first source of energy comes simply from cooling. As Earth radiates heat into space, the core must lose some of its own warmth, driving convection. This secular cooling is constant and relentless. Billions of years of slow exhalation. But it won't last forever. Cooling alone would eventually stall the currents, freezing the core from the inside until the dynamo choked on cold metal. That is where the second calorie appears: latent heat. Every atom of iron that solidifies onto the inner core releases a little burst of warmth. Multiply that by quadrillions upon quadrillions of atoms forming over hundreds of millions of years, and this invisible energy becomes significant. Another push that keeps the core flowing. The third calorie is the most surprising: chemical buoyancy. When iron freezes, it rejects impurities, lighter elements like silicon, oxygen, and hydrogen. Those expelled atoms rise upward like tiny life rafts in a molten sea, further mixing the core. It is a quiet force with loud consequences. The dynamo lives because the inner core continues to grow, restoring strength to a field that may otherwise falter. Yet these power sources face relentless obstacles. The mantle above the core acts like insulation, thick and sluggish. When continents cluster over the core mantle boundary, they trap heat below them, slowing the rate at which the core cools. Subducted slabs, cold, sinking plates, can puncture that insulation, increasing heat flow in scattered patches. The boundary is not a smooth radiator, but a chaotic quilt of hot and cold, throttle and brake. Plate tectonics, water, atmospheric stability, all are tangled in the geodynamo's fate. Without liquid water and a breathable sky, plate movements might slow. Without moving plates, heat would stagnate. Without heat loss, the dynamo would die. And without the magnetic field, solar wind might strip the atmosphere bare, oceans could fade into space, life would face cosmic exposure. Everything depends on everything. Earth somehow found the razor's edge. Just fast enough heat loss to keep the core stirring, just enough insulating balance to prevent the inner core from freezing too soon. A self-regulating system emerged, a delicate choreography between rock, metal, ocean, and air. Each component clueless on its own, but together achieving equilibrium that seems far too generous to be accidental. The dynamo's diet is not a feast. It is a strict rationing, a careful ledger of energy earned and energy spent. Its survival is improbable. Its endurance, astonishing. Yet here we are, protected by a shield we cannot touch, powered by a furnace we will never see, and sustained by a planetary metabolism that should break, but doesn't. The mantle is not a quiet blanket. It is a restless, churning quilt of minerals and molten seams, stitched together by pressure and torn apart by time. Slow though it may seem, creeping inches per year, it is always in motion, rising and sinking in grand convection currents that move continents, build mountains, and open oceans. This silent circulation acts as the bridge between the deep furnace of the core and the cold of space. Without it, heat from below would stagnate. With it, the core can breathe. But the mantle is not uniform. It transforms with depth, shifting its minerals into tighter and stranger arrangements as pressures increase. Upper mantle rocks may flow like thick taffy, while those deeper down behave more like glassy tar, dense and unwilling to budge. Water dissolved within minerals softens some regions, letting them slip more easily, while iron-rich patches absorb heat like thick wool. This patchwork of traits makes the mantle a complicated negotiator, controlling how much heat the core is allowed to lose and where. Subducted slabs, the cold remains of long-dead ocean floors, plunge downward into the mantle. Some reach the core mantle boundary, cooling its surface in vast, irregular patches. Those regions act like drains, siphoning heat from the metallic ocean below, boosting convection and strengthening the magnetic field. Meanwhile, other areas act like insulation. Massive, dense thermochemical structures, larger than continents themselves, sit above the core like thick blankets, choking the escape of heat. These giant formations, called LLSVPs, may have persisted for billions of years, shaping the rhythm of the geodynamo from far above. Between these colossal piles lie zones where seismic waves suddenly slow, as if entering a swamp. These ultra-low velocity patches may be partly molten rock or emulsified mixtures of silicate and iron, tiny fragments of core that splashed upward long ago. Some scientists suspect these strange pools could harbor the ingredients for new plumes, the deep-seated thermal jets that punch upward into the crust, erupting as volcanic hotspots like Hawaii or Iceland. Heat from the core leaks into the mantle not in a smooth and steady sheet, but through chaotic portals, no two alike. Every variation in mantle texture changes the story of the core. Tug too hard on one part of the quilt, and the heat flow spikes, possibly spurring magnetic unrest or triggering a reversal. Let insulation thicken, and the dynamo could weaken in response. The mantle's behavior becomes climate for the metal ocean below, an internal weather system we can only observe through seismic shadows. For all its crushing weight, the core is the more delicate partner in this relationship. Its magnetic field depends on precise conditions that the mantle may enhance or sabotage without ever realizing it. Yet Earth has somehow balanced these competing forces. Rocky shells shifting and swirling above, metallic tides circulating below, each influencing the other in a feedback loop that sustains both geology and habitability. The mantle's quilt is imperfect, asymmetric, and forever changing. But somehow, its mismatched patches and tangled threads have kept the heart of our world beating. Through tempests of fire and eras of ice, through reversals and renewals, through all the improbable ages of Earth. Without this rocky sky, the liquid core could not endure. Without that molten heart beneath it, the planet would be defenseless. They are partners locked in a restless dance, each shaping the other's fate. Mars offers a quiet warning. Today, it is a cold world. Its surface stripped by radiation, its thin atmosphere blown away by the solar wind. But long ago, Mars had a magnetic field of its own. Ancient rocks on its highlands carry faint fossil magnetism, whispers of a protective shield that once encircled the planet. Something kept Mars's core alive in its youth. But that engine eventually sputtered and died. To understand why Earth thrives while Mars slumbers is to see how narrow the path to a living core truly is. Size is the first culprit. Mars is just over half Earth's diameter, and much smaller worlds lose heat quickly. Its molten heart would have cooled faster, convection slowing until the liquid metal grew sleepy and still. Without enough heat escaping through the mantle above, the core could no longer spin its magnetic threads. Even a once boiling sea can freeze if the fire beneath it dwindles. Composition compounds the issue. Mars likely formed with more sulfur in its core, an element that lightens metal, lowers its melting point, and perhaps encourages stratified layers. A stable lid may have formed at the top of Mars's core, a boundary that blocked fresh convection from reaching the center. Iron could still be molten below, but trapped beneath a stagnant cap, unable to churn and generate a field. The core did not freeze fully. It simply stopped moving. Then comes the greatest difference of all: tectonic stillness. Earth's continents wander, colliding and ripping apart, dragging cold slabs deep into the mantle and pumping heat upward. This constant recycling pulls warmth from the core, forcing it to release energy and keep flowing. Mars, however, hardened early. Without tectonic motion, heat flow dwindled. Mantle plumes may still sputter beneath the surface. Olympus Mons stands as proof of ancient power. But they no longer cool the core fast enough to sustain motion. Venus adds another twist to this cautionary tale. Nearly Earth's twin in size and mass, it should have a vibrant dynamo. Yet today, Venus's magnetic field is almost non-existent. Thick atmosphere, no plate tectonics, sluggish cooling. These conspire to smother the core, leaving it too warm and too still. Where Earth threads the needle, cooling just enough, but not too quickly, Venus missed the mark in the opposite direction from Mars. Examining these two worlds reveals the precarious balance Earth has maintained. Too small, like Mars, and the dynamo dies of starvation. Too insulated, like Venus, and the dynamo suffocates beneath its own heat. Earth sits in the middle, a body large enough to retain its fire, but restless enough to bleed energy into the mantle above. A planet not too cold, not too hot, but dynamically just right. Our core should not persist as it does. Physics alone does not ensure survival. Earth needed plate tectonics, water to lubricate the surface, radiogenic elements heating the mantle, and a history of violent collisions that mixed its ingredients into just the right blend. It needed luck. Mars is the reminder of what happens when luck runs thin. A world with once beating heart, now silent. A survivor of the same solar nursery, yet shaped by a fate so different. And hidden in that silence lies a message for us. The magnetic shield that guards every breath and every ocean here on Earth is no birthright. It is a fragile gift, one that must be earned, maintained, and never taken for granted. Nickel is the quiet companion, rarely the star of the story, yet always beside iron, steady and loyal. If Earth's core is a grand metallic symphony, iron plays the bold brass section, booming with heat and motion. Nickel, meanwhile, is the violin line woven through the background, subtle, essential, and easy to overlook. But ignore nickel, and the music falls apart. In the primordial furnace where Earth formed, iron and nickel were the most compatible metals, cosmic siblings forged in supernovae. When molten metal pooled to the planet's center, nickel didn't hesitate. It followed iron downward, becoming a permanent resident in the core. Today, roughly 1 out of every 10 atoms in the core is nickel, a minority, but a powerful one. Like a skilled conductor, nickel tweaks the performance of iron in extreme environments. It adjusts melting points just enough to help maintain a liquid outer layer, while allowing the inner core to crystallize at its heart. This delicate tuning may be one reason the core sustains a molten engine instead of freezing solid too soon. Nickel also alters how light elements dissolve, affecting which impurities can hide within the alloy and which are pushed out to drive convection. Without nickel's influence, oxygen might dissolve too greedily or sulfur not enough. The ratio matters, because chemistry is destiny at the planet's center. Consider the inner core's crystalline structure, those iron atoms crushed into patterns that determine how seismic waves pass through. Nickel stands among them, stabilizing certain phases over others. Perhaps it encourages the hexagonal close-packed alignment that produces the seismic anisotropy scientists detect. A faster pulse along the poles than across the equator. Nickel doesn't claim credit, but the evidence traces a subtle signature back to its presence. Meanwhile, nickel supports the geodynamo with another trait. It strengthens conductivity. A more conductive metal ocean means magnetic fields can build and stretch farther before fading. It means currents can churn with less resistance and more stamina. Nickel, by simply being itself, makes the dynamo more resilient, more enduring, more difficult to silence. To probe nickel's deep contributions, scientists conjure miniature cores in laboratory chambers smaller than a fingernail. They crush metal alloys between diamonds, blast them with lasers, and measure how waves ripple through microscopic samples. In those tests, nickel reveals how it bends iron's rules, tiny nudges that become tectonic consequences on the scale of a planet. Mixed nickel with silicon, oxygen, sulfur, or carbon under pressures millions of times that at the surface, and the behavior shifts again. Phase diagrams. Maps of what structure forms under what conditions. Begin to resemble complex works of art, with nickel's influence reshaping every border and curve. It is chemistry written in the script of stars, rehearsed now beneath our feet. Nickel does not roar like iron or whisper like hydrogen. It harmonizes. It ensures the core's symphony continues, bars flowing into bars over billions of years, long after simpler worlds have gone silent. Without nickel's note, Earth's core might have frozen early, or thinned into instability, or dimmed into magnetic exhaustion. Instead, it plays on, steady, improbable, alive. Because even the quietest performer knows exactly when to carry the tune. Just above the liquid outer core lies a realm we barely understand. A hidden borderland where physics turns cryptic and the planet guards its secrets in silence. Seismic waves traveling through this region slow and bend in unexpected ways, hinting that the metal ocean doesn't rise cleanly into the base of the mantle. Instead, a strange layer may float there, thin, stably stratified, and chemically unlike what churns below it. This is the top of core mystery, a lid that should not exist, and yet might. Traditionally, we picture the outer core as a freely convecting sea of molten iron alloy, every drop swirling to sustain the magnetic field. But some data suggest a quieter surface, a layer where fluid sits still, unmixed. How could such calm exist above such chaos? One idea imagines iron snow. As the core cools, tiny crystals might form near the top instead of the center. Flakes of solid metal that drift downward like metallic snowstorms. When they melt again at depth, the chemistry becomes uneven, layering the top with lighter ingredients. Over time, this chemical mismatch could produce a stratified lid, a stagnant skin over the churning abyss. Another theory points upward. Perhaps the mantle has been leaking into the core. Subducted slabs, fragments of ancient seafloor, may deliver oxidized material deep enough to mix with core metal. Or plumes rising from the boundary might erode patches of mantle rock into the molten alloy. The result would be zones enriched in light elements, not enough to sink, not eager to mix, just different enough to float quietly above the currents. However the layer forms, its existence carries consequences. Convection is the lifeblood of the geodynamo. A stable lid smothers motion directly beneath the core mantle boundary. Fluid below must find longer, deeper pathways to circulate. That changes the patterns of magnetic uplifts that reach the surface, shaping how the field wobbles and drifts over decades. Sudden geomagnetic jerks, pulsating hotspots of magnetic flux, the slow reversal of fields. These might be signatures of a core whose roof is unevenly sealed. Yet the puzzle deepens. If the lid is too strong, the dynamo starves. The magnetic shield would weaken, and the core could stagnate. Somehow, Earth seems to have struck a balance. For billions of years, heat still escaped fast enough to keep metals moving, even if the top layer sometimes resisted the flow. Perhaps the lid isn't permanent at all. Mantle plumes rising like torch flames from deep below could break the stratification, stirring the quiet metal into turbulence again. Subducted slabs could cool one region enough to peel the layer away. The quilt above and the furnace below are always negotiating. Sometimes the core sleeps beneath a blanket. Sometimes it throws the blanket off. We listen for hints in the magnetic field as it drifts and distorts, a compass trying to reveal the invisible weather beneath our continents. And through seismic shadows that ripple up from deep earthquakes, we trace the outlines of something smooth, still and eerie at the core's top. In that silence lies a paradox, a layer that calms the chaos just enough to let the engine run, never fully quiet, never fully free. A veil between worlds, covering a heart that refuses to stop beating. Heat is always on the move. In the core, it rushes outward like steam escaping a kettle. But instead of air, it enters a mantle made of slow-moving stone. To keep Earth's magnetic field alive, this heat cannot simply seep out quietly. It must drive motion. It must stir metal into currents strong enough to build a shield around the planet. But heat has two different ways to travel: conduction and convection. One is calm, the other is wild. Conduction is the silent method. Atoms vibrate, passing energy along like a whispered secret from one neighbor to the next. No movement of the fluid itself, just an invisible relay. If iron at the core conducts heat too well, energy may escape without lifting a finger. No churning, no circulation, no magnetic field. For decades, scientists believed conduction in the core was modest, leaving plenty of energy for turbulence. But recent experiments changed everything. By squeezing iron alloys at extreme pressures and heating them to thousands of degrees, researchers discovered that core metal conducts heat far more efficiently than expected. Suddenly, the whisper became a shout. If conduction carries too much of the burden, convection may not be required, and the core could drift toward stagnation. The magnetic field, our guardian against solar wind, would suffer. This revelation cast doubt on the core's long history of activity. How has it continued to convect for billions of years? Why hasn't the dynamo died? The answer came from chemistry. Specifically, what happens when the inner core grows? As solid iron crystallizes, it pushes lighter elements outward. Think of droplets of buoyant fluid rising through denser liquid, like ghostly lanterns. This compositional convection provides energy independent of temperature. A second engine. Rising plumes of light metal, sinking rivers of heavy metal, twisting together into a restless cycle. Even when conduction steals heat from the system, these chemical forces step in to keep the dynamo alive. Visualize the core not as a single swirling mass, but as layered motion. Hot, iron-rich currents shoot upward. Cooler streams fall back around them. Microscopic eddies spin like dancers at the edge of the turbulence. Each pattern changes the magnetic field above, tugging at compass needles, shifting the auroras, and occasionally flipping the poles entirely. A planetary ballet performed without an audience for nearly all of Earth's history. In this finely tuned performance, everything matters. How fast Earth cools, where heat escapes into the mantle, how quickly the inner core freezes, and what impurities blend into the mix. If any one factor slips too far out of balance, conduction could smother the motion and silence the dynamo. But so far, the core has adapted. It has diversified its energy budget. Thermal buoyancy may flag at times, but chemical buoyancy rises to help. The inner core itself becomes both anchor and fuel, feeding the engine that protects the surface world. Heat is stubborn. It refuses to sit still. And deep in that metallic sea, stubbornness is survival. The core continues to circulate against the odds, because even in silence, heat is always searching for a way out. Rocks are memory keepers. Long after storms dissolve and mountains crumble, tiny magnetic grains inside them continue to point toward the poles of a world that may no longer exist. These minerals, often just iron-rich specks suspended in cooled lava, freeze like compass needles in mid-gesture, sealing the direction and strength of Earth's magnetic field at the moment they formed. They are Earth's oldest photographs, taken not with light, but with magnetism. When lava erupts onto the surface or seafloor, it begins as a glowing liquid, with magnetic domains jostling freely. As it cools, those domains line up with the field threading through the planet and then lock in place as the rock solidifies. Later, that rock might be buried, tilted, or transformed. But unless heated beyond a critical temperature, its magnetic memory stays intact. By collecting and analyzing such stones, ancient basalts, baked sediments, crystals grown in deep time, scientists reconstruct the flickering heartbeat of the geodynamo across billions of years. The earliest hints of a magnetic field appear in rocks older than 3.4 billion years. Some studies push the date even further back, suggesting strong fields soon after Earth's surface cooled enough for crust to form. If true, this is astonishing. The inner core is far younger than that. Its crystallization likely began well after these early rocks recorded a functioning dynamo. So what powered the engine in the beginning? Chemical buoyancy, born from the initial separation of metal and rock, is the leading answer. As iron sank into the forming core, light elements like oxygen and silicon were left behind or expelled upward. This created density differences big enough to force the liquid metal to churn. In those violent early ages, convection needed no help from freezing iron. The core boiled with energy, and the magnetic field surged outward, strong, chaotic, alive. Yet the record isn't smooth. Some rock archives suggest quiet periods when the field weakened, flickered, or nearly died. Perhaps heat flow briefly dipped below the threshold for convection. Perhaps mantle insulation temporarily smothered the dynamo's breath. But in nearly every case, the field returned, persistent as tide and heartbeat. Not all rocks agree on the details. Alteration from later heating or fluid intrusion can scramble their signal. Some ancient samples contain magnetic grains too coarse or too fine to faithfully record the field. Scientists must sift the genuine memories from the forged or forgotten ones, using microscopes, magnetometers, and careful experiments that reverse time grain by grain. Still, a picture emerges. Earth's magnetic shield switched on early, long before life needed it. And it kept returning, even during its feeblest phases. That endurance deepens the core paradox. The geodynamo had to survive billions of years of shifting conditions, including the lull before the inner core began freezing. It managed, with chemistry as its early lifeline, with thermodynamics learning to stand beside it later. Every ancient magnetic signal is a message that says, the impossible persisted. The core did not sleep for long, and the rocks that hold its voice remind us that this protection has guarded Earth for almost as long as Earth has existed. A continuity so unlikely it feels almost intentional. Each stone is a quiet witness, whispering across a deep time. The field has been here, longer than anyone should expect. Deep in the center of the world, beyond the magma ocean, past the crushing mantle beneath the liquid iron tides, lies a crystal heart that is not one heart at all. The inner core, once imagined as a single solid sphere of iron alloy, now reveals layered secrets. Seismic waves traveling through it, those subtle ripples launched by earthquakes, behave differently depending on direction and depth. The signals are faint, but together they suggest something astonishing. A heart within a heart. Scientists call it the innermost inner core, a region only a few hundred kilometers wide, distinct from the layers around it. What could cause such a hidden partition? One idea begins with time. The inner core didn't exist at Earth's birth. It began as a seed only after the core cooled enough to allow iron to solidify. As crystallization continued outward, conditions changed. Pressures rose. The distribution of lighter elements shifted. Even Earth's spin rate evolved. In that shifting environment, iron atoms might have been forced to rearrange themselves, rotating their alignment like dancers following a new rhythm. The earliest formed iron crystals, the innermost inner core, may preserve a memory of the world's first cooling steps, while the outer portion embodies a later, altered chapter. Another possibility lies with chemistry. As the inner core grows, it rejects impurities, silicon, oxygen, sulfur, and others, into the outer core. But what if the mix of impurities drifting through the liquid changed over time? A shift in chemistry would alter how new crystals attach themselves to the growing core, producing different textures and orientations. Seismic waves would notice, even if humans cannot. There are clues that the inner core doesn't grow evenly. Seismic data hint that one hemisphere may be crystallizing faster than the other, an imbalance that could twist and deform the solid metal inside. Over millions of years, such uneven growth might cause iron crystals to stretch and rotate, aligning themselves in a preferred direction. If a new alignment overtook an older one, the boundary between them would become the two-tone heart scientists now attempt to decipher. Rotation adds yet another twist. The inner core may spin slightly faster or slower than the mantle above it, caught in a tug-of-war between electromagnetic forces and viscous drag. A change in rotation, perhaps from a shift in mantle convection or major reconfiguration of tectonic plates, could reorder crystal structure, carving the innermost inner core into existence, like a scar of motion frozen in metal. All of these scenarios share one truth. The inner core is alive with history. Its fabric is not a uniform brick of iron, but a diary written in lattices and grain boundaries. Each orientation is a sentence. Each crystalline shift is a turning point. It remembers when the dynamo ran on chemistry alone, when it switched to the power of freezing metal, when the mantle above pulled harder or softened its grip. The existence of a layered core, complex, dynamic, diverse, makes its persistence all the more remarkable. Systems this delicate usually fail long before billions of years pass. Yet Earth's inner core has grown, reorganized, and persisted through every challenge the planet has thrown at it. A two-tone heart beats below us. It should have stumbled. It should have stalled. But instead, it continues its silent work, keeping the field alive, keeping the sky intact, keeping us here to imagine what lies in the darkness below. Far below the continents and oceans, the engine that sustains our magnetic shield continues its quiet rotation. But no engine burns forever. Heat is a finite inheritance, and the core has been spending that inheritance since the day Earth was born. Every year, every second, the planet cools a little more. The inner core grows thicker as the liquid metal around it surrenders heat and crystallizes. Convection, once furious and wild in the early Earth, becomes gradually calmer. The question that lingers like a distant echo is simple, yet profound. How long can this heartbeat last? To glimpse the future, scientists build models, mathematical glimpses into what might come next. They track the core's energy budget, the latent heat released as iron freezes, the buoyancy supplied by expelled light elements, the thermal pressure from the mantle above. These forces will not remain constant. As the inner core expands, the reservoir of liquid metal shrinks. The buoyant stirrings weaken. Meanwhile, the mantle continues to cool at its glacial pace, pulling heat from below, but changing how easily that heat can escape. Nothing about this engine stays the same. Far ahead in time, billions of years beyond our age, the system will shift. The inner core may someday reach a point where freezing slows dramatically. If most of the outer core becomes solid, convection will falter. Chemical buoyancy will diminish. The magnetic field could weaken, becoming patchy and unstable. Auroras may fade. Shielding may thin. Solar wind would begin peeling away the atmosphere grain by grain, and Earth would start to resemble the quieter, lonelier fates of Mars or Venus. And yet, paradoxically, these projections extend farther into the future than our sun's own stable lifespan. Long before the dynamo grows silent, the sun will swell into a red giant, flood the inner solar system with overwhelming heat, and strip away oceans and skies. In that distant era, whether the geodynamo persists or stutters may no longer matter to any creatures living at Earth's surface, if any remain. But destiny need not be singular. There are branching paths. If plate tectonics continues, its cooling handshake with the core will endure, keeping the dynamo fed. If subduction slows or continents lock into a stagnant lid, the mantle might insulate the core too well, accelerating magnetic decline. Conversely, if mantle plumes intensify or water cycles evolve, heat flow patterns could shift again, stirring new rhythms in the fluid iron. Even chemical complexity offers surprise. A stratified layer at the core's top might one day collapse, injecting a rush of buoyant energy into the dynamo, an unexpected revival. Or new phase transitions at crushing pressures could rewrite iron's behavior entirely, granting fresh fuel to a system long thought to be fading. The end of the magnetic field is not a cliff. It is a dimming horizon, a soft diminuendo. Earth's core has defied expectations for nearly 4.5 billion years. And its resilience suggests it may yet outlive predictions we make today. The same unlikely balance that kept the field alive through ancient storms and tectonic transformations may continue to perform its quiet miracles, long after we have ceased to notice its strength. Some engines die violently, others simply slow. Our world's heart will keep beating for a long while yet, its tempo steady, its power subtle, its persistence a quiet defiance of the odds. Even as the light of the sun grows harsh and unfamiliar, deep in the darkness below, a crystal heart will still be growing. and the metal ocean around it will whisper its final currents into the fading night. Beyond our solar system, thousands of worlds circle other stars. Strange silhouettes glimpse through dimming starlight and subtle gravitational wobbles. Their skies might glow emerald. Their oceans may be methane or ammonia or liquid diamond. Their mountains could be made of iron. With every new discovery, one question rises like a tide. How many of these alien planets have metallic hearts that beat like Earth's? How many host dynamos, shields against the violence of their suns? To answer that, we must translate Earth's improbable survival into a recipe. It is not a simple one. First, the planet must be big enough. Too small like Mars or Mercury, and the core cools too quickly, locking metal into stillness. But too large, like the super-Earths with crushing gravity, and pressures climb so high that iron may freeze throughout, leaving no liquid layer to twist a magnetic field into existence. A world must carve out the narrow territory between these extremes, large enough to keep heat trapped, yet restless enough to let that heat escape. Then there is the mantle's role, its convecting churn, its willingness to cooperate with the core beneath it. A planet must shed heat from its interior in a controlled chaos. Plumes rising, plates shifting, continents itinerant. Without mantle mobility, a dynamo is orphaned. And without water, yes, water, plate tectonics itself may never awaken. This simple molecule may dictate whether a planet breathes or suffocates under geological stillness. Next, we consider chemistry. Iron will gather into a core, but what else arrives? Light elements change everything. Too much sulfur, and a stagnant layer may corral convection into shallow tides. Too much oxygen or silicon, and the core grows too light or freezes too strangely. Hydrogen, carbon, nitrogen. Each one writes a different phase diagram under crushing pressure. Their combinations create cores that behave like nothing in our laboratories. Some worlds may never form traditional iron oceans at all. Carbon-rich planets, born in star systems flooded with graphite and carbide, might boast cores made of molten iron carbide, with diamond crusts gleaming under alien skies. These planets could sustain magnetic fields powered by chemistries we barely understand. Forbidden cores, according to Earth's rules. Yet they may exist in abundance across the galaxy. Water worlds, wrapped in deep oceans and high-pressure ice layers, may hide metal hearts far below layers of supercompressed water. The geometry of such worlds might trap heat differently, making convection either unstoppable or impossible. In such places, a magnetic field could be weak yet constant, or violently intermittent. For every constraint that seems absolute, an exoplanet arrives to defy it. Some worlds orbit red dwarfs, bombarded by flares that test the strength of any magnetic shield they possess. Others exist in darkness, far from warming light. Yet geothermal heat alone may keep their cores roiling. There are giant rocky planets with iron proportions that dwarf Earth's. There are ones so depleted in metals that their cores are tiny, feeble sparks struggling in the dark. The universe is a kitchen of endless experiments. Iron and nickel are not rare ingredients, but how they melt, stratify, and freeze depends on local recipes. Stellar chemistry, planet mass, formation violence, cooling rhythm. Earth's core should not exist this way, and yet it does. And if nature found a path here, it may have found many paths elsewhere. On distant worlds, beneath alien skies, invisible shields may rise and fall. Metal oceans may twist and thunder with silent lightning. And somewhere, perhaps, life looks up at auroras dancing across its sky, unaware of the molten miracle beneath its feet. Earth is no longer the exception. It is a clue, a message written in magnetism, telling us that impossible cores may be common, and that the universe may be far more welcoming to hearts of metal than we ever dared imagine. Shouldn't exist doesn't mean impossible. It means improbable. It means the core we depend on is the survivor of 1,000 failed scenarios, a solution that nature almost missed. Earth's center is a balance beam over an abyss. Too hot and everything melts without structure. Too cool and everything freezes into silence. Too insulated and convection dies. Too leaky and the inner core forms too fast. Too pure an iron heart and density breaks the seismic rules. Too impure and it loses the strength to spin a shield around the planet. Every parameter is a razor's edge. Chemistry, pressure, cooling rate, mantle behavior, all having to align over billions of years. And yet they did. The story began with iron rain. Micro-droplets sinking through a violent molten world, efficiently segregating metal into the depths, when physics said the planet might never melt enough for such thorough sorting. Then came the moon-forming impact, a catastrophe that should have fragmented the Earth beyond recovery, yet instead reset its interior and gave it angular momentum, strengthening the dynamo's future. A magma ocean cooled, not too fast, not too slow, finding the one thermal runway that allowed liquid metal to remain while the mantle solidified above. Inside that dark ocean of iron, chemistry refused to stand still. Light elements infiltrated the core, making it too buoyant to freeze entirely and too dynamic to rest. Sulfur softened the melting curves. Silicon adjusted sound speeds. Oxygen and hydrogen whispered from ancient water. Carbon slid between atoms like a ghost, tipping the balance one more crucial degree. Nickel tuned the phase of iron, a supporting musician keeping perfect pitch. The inner core itself arrived late, a child of the planet's middle age. Its birth reignited the dynamo when thermal forces alone began to tire. Crystallization became a second engine, and chemical snowstorms rose toward the mantle above. Even the texture of its crystals, aligned by flow, rearranged by shifting rotation, became a fossil record of Earth's interior weather. Above it all, the mantle acted as both enemy and partner, insulating, feeding, throttling, and rescuing the dynamo depending on geometry and time. Plate tectonics kept heat flowing just fast enough. Water helped the plates move, and continents drifted in patterns that modulated energy extraction from the deep. Every thread, violent beginnings, delicate cooling, risky chemistry, mantle chaos, twisted into one unlikely rope capable of spanning 4.5 billion years. And from that rope depended everything that breathes. Without the core's magnetic shield, solar wind would strip the atmosphere like leaves in a storm. Without the atmosphere, oceans would vanish into space. Without oceans, life would be a whisper at best, if it began at all. The entire history of animals, forests, coral reefs, flight, civilization, all of it dangles from a furnace that keeps refusing to go out. Calling it something that shouldn't exist is not exaggeration. It is gratitude. It is awe. It is the recognition that planets are fragile, contingent wonders. Studying this improbable success is not just about knowing our past. It is about understanding our luck, our vulnerability, and our responsibility to the only world we know with a beating metallic heart. Because everything we are, down to the last breath, was forged by the fire that should have gone cold. At the very center of everything we know lies a place no human will ever see. A sphere of iron alloy, glowing hotter than the surface of the sun, compressed by the weight of the world into a crystalline core. It spins in darkness, alone, unseen, unending. And yet, From this buried heart flows every magnetic whisper that protects our skies and shapes our history. A sun beneath our feet, burning without flame. It is a lullaby of motion. Liquid metal streams rise and fall around the solid seed, swirling into invisible storms that generate the magnetic field. These currents do not roar. They hum. They hum through seismic tremors that ripple outward from earthquakes. They hum in the auroras that shimmer like curtains over the poles. They hum in the steady confidence of a compass needle. That small technology rooted in something unimaginably vast. The contradictions we've uncovered, the iron that melts yet freezes, the heat that must escape yet remain, the chemistry that divides yet unites, are not imperfections. They are the very reason the system works. Earth's core survives because it is complicated. It persists because its stability comes from delicate imbalances that constantly correct one another. Every atom at the center of the planet is a survivor of fire and collapse, of supernovae long dead, of collisions unimaginably fierce. Those atoms found their way here, gathered into a heart that refuses to flicker. Long after continents have reshaped 100 times, long after mountains crumble into sand and seas trade places with deserts, the core will still be turning, writing its story one crystal layer at a time. There is comfort in that. To know that beneath every footstep, beneath every home and forest and ocean, there is a steadying presence, a furnace that keeps the cold of space at bay, not through heat alone, but through magnetic grace. In sleep, while storms howl above and tides crash against shores, the hidden sun keeps watch. It reminds us that life depends not just on sunlight from above, but on fire from below. That habitability is an orchestra, not a solo. That survival often relies on things quiet, concealed, and easily forgotten. So if one night you find yourself far from city lights, staring up into a sky strung with stars, worlds with their own buried hopes and silences, remember that our world glows from both directions. The stars burn above us. The core burns beneath us. Between those two flames, a thin layer of miracles unfolds. Oceans, trees, language, love. Us. The core should not exist in such perfect balance, and yet it does. It has for billions of years, and may for billions more. Long after we are gone, long after the sun expands, and the story of Earth enters its final chapters. It will keep spinning, not for us, but because that is what hearts do. A lullaby for a hidden sun, a warmth we never see, a gift we rarely notice, and a quiet promise that the world, in all its contradictions, can hold together, beautifully, impossibly, through the darkness.